Hello, I'm Konar Skindlov. Today I'll be presenting to you the research that I did at Carroll College in the summer of 2019 with Dr. Kessler. The name of my poster is the metalation of Pyrrole-Based NNN-Pincer Ligands with heteroaromatic donor substituents. Here's my poster. So this research was guided by the principles of green chemistry, which act to reduce waste and environmental harm done by chemical processes. We specifically tried to do this by creating metal complexes that would act as catalysts in chemical reactions. A catalyst is a chemical compound that decreases activation energy so a reaction can proceed more quickly. One specific area of green chemistry that we were trying to adhere to was atom economy. Now, atom economy is an act of trying to get the highest percent of atoms in your reagents you use in a chemical reaction incorporated into the desired product, reducing byproducts. Catalysts are very good at this because reducing the activation energy allows for less reagents used overall, and a catalyst is regenerated at the end of a chemical reaction, so it can be used more than once for further reactions. And a reagent is just any chemical used in a chemical reaction. Another way we tried to adhere to green chemistry was the use of metal complexes within the first row of the transition metals. Transition metals are the D block rectangle between the left column of earth metals and the right column of non-metals on the periodic table. So first row transition metals are more abundant and environmentally friendly than second and third row transition metals, or the precious metals. First row transition metals include metals such as iron, nickel, and copper. Since they're more abundant, there will be less time spent trying to mine these metals, which will also reduce pollution in that way. And we use pincer ligands for this research because they coordinate to the metal complex through 3 different coordinating sites and result in the highly stable complexes. The specific ligands that we chose, shown here, are our NNN-pyrazole and our NNN-trz. We use this abbreviation NNN because we plan to coordinate the metal, which would sit in the center of these 3 nitrogens right here. So NNN and then pyrazole is a name for the substituent arm that this particular ligand has, and this one is triazole with its triazole substituent arm. So the Pyrrole base is an organic molecule, and it makes up the base of the ligand, as I just stated. And we use this structure for the ligand because it is similar to porphyrin, which is a part of an important enzyme called catalase, which catalyzes the decomposition of hydrogen peroxide into water and oxygen. And this enzyme is used in almost all living things that are exposed to oxygen. Now, an enzyme is what we call nature's catalyst. They're very efficient at reducing activation energy of particular reactions, and a lot of these reactions help keep us alive and let our body function, living things function. So in order to model our catalysts that we're synthesizing to be the most efficient that they can be, we try and model after these enzymes because of how efficient they are in nature and how well they do their job at catalyzing reactions. So these ligands are also expected to be redox active, so they can perform oxidation reduction reactions. And they have performed proton coupling electron transfer reactions, which occur naturally in respiration and photosynthesis, and nitrogen transfer reactions, which an example is shown here in figure 2, where porphyrin with a cobalt center is doing a nitrogen transfer reaction. So let's get to the results of my research. The first thing that I had to do was synthesize the ligand from a literature protocol and purify it so we knew that we had the most pure ligand that we could for our metalation reactions. As shown here are 2 schemes of reactions, scheme 1 and scheme 2. The only difference being the starting ligand. Up here we have our NNN-pyrazole, and below we have our NNN-trz. And then in step 1 of scheme 2, we have N2 listed because we did most of these reactions for triazole in a nitrogen atmosphere. So both of these schemes have 2 steps. First step including the solvent, base, 30 minutes, and room temperature, and the second step saying metal and overnight. In the first step, I would take our ligand that we were working with, whether it be the NNN-pyrazole or NNN-trz. I would dissolve it in the solvent and add a base This base was added to try and remove this Pyrrole hydrogen right here, so that the metal, once we added it, could hopefully coordinate to these three positions, NNN, or in this case of triazole, which I did most of my research on, NN and N. So after we added that base, we'd let it stir for 30 minutes at room temperature, and then once the 30 minutes was up, we'd add our metal and let it stir overnight or over the weekend, depending on the day that we were working on in the week. So the variables, as you can see, I have table 1. We have different variables that were changed in order to try and optimize metallation conditions for this reaction. My first reaction was done from literature protocol, which used the triazole ligand, acetonitrile ACN solvent, triethylamine NET3 base, and metal precursor PDCl2, and a nitrogen atmosphere. So we tried this, and it has been successfully done as proved by literature, but we could not successfully do it in our lab. So we had to try and change up the solvents, base, metal precursor, and the atmosphere to see if we could get better conditions in order to actually get our ligand metallated to our metal precursor. Very quickly, we were able to figure out that our N2 atmosphere was the optimum atmosphere over air. And the difference between these two, some reactions could be air sensitive, where the oxygen in, just the oxygen in the air or the oxygen in water vapor could react with either the ligand or the metal before the two could react with each other, which would obviously not create our desired product that we were looking for. So after we tried a few in the air, we realized through our NMR analysis, where our NMR, it's an chemical instrument that pulses the sample with electromagnetic waves that results in signals for all unique H atoms on the molecule, hydrogen atoms, whose chemical environment can be analyzed on the basis of its chemical shift or splitting pattern. So in the case of triazole here, since this ligand molecule is symmetrical down the middle right here, down the middle, this hydrogen, there would be one hydrogen here, two hydrogens here, one hydrogen here, and one hydrogen here. And then the hydrogen right here at the Pyrrole base on the Pyrrole nitrogen. So since it's identical, the only unique hydrogen peaks we would have for the ligand would be this hydrogen, and these two have the same chemical environment, so they would be seen as one peak with a different splitting pattern. This hydrogen, this hydrogen, this hydrogen, and this hydrogen. So we'd have 5 different hydrogens for a free ligand of triazole. And by our NMR analysis, we could see that our N2 environment was more optimal than our air environment in just a regular glove box, or a regular hood, excuse me. So down here in table 1, as I stated earlier, are our listed solvents, bases, metal precursors, and atmosphere that we used. And all of these have been used with different bases and solvents and so on and so forth to try and find optimum conditions. Unfortunately, many of our reactions were unsuccessful, but we did get one unexpected product in a reaction with the triazole ligand. NMR shown here on top. Figure 4a is our NMR of the unexpected product we got from the triazole reaction, which included the triazole ligand in methanol solvent, MEOH, with the PDCl2 precursor and potassium terbutoxide base. So one thing that we can see immediately is that we have many more peaks up here in figure 4a for the product than we do with the free triazole ligand down here. As I stated before, we would have 1, 2, 3, 4, and I believe 5 right here for the hydrogen, unique hydrogen peaks for the triazole ligand. These 2 peaks over here are just impurities we can unfortunately not get out for the NMR. So as I stated, there are many more peaks up here, which is really interesting because even if we had the metal coordinated to the center of this ligand, we would be able to still have this symmetry of the molecule that we had previously, except we would be losing one hydrogen peak because hopefully we had the metal coordinated to these 3 nitrogens, so this hydrogen would have no place to be bonded to that nitrogen. So the idea that we have more peaks up here is very interesting. And one thing I need to note is that this NMR for the product up here was taken in chloroform D CdCl3 solvent, while the bottom was in deuterated DMSO, dimethyl sulfoxide. So we can't compare the chemical shifts, but we can still compare the number of peaks because that only correlates to the number of hydrogens. So this is very interesting because we see this, but we don't expect this to happen because, as I stated, we want that symmetry to still be in the molecule. So one hypothesis that we have come up with is that we possibly could have, I'll go back to a ligand, possibly could have coordinated the metal to the Pyrrole nitrogen as well as one arm of the ligand, which would cause the chemical environment for the hydrogen on each arm to be different since one is coordinated to the metal and one is not. So with this, as I stated, to conclude, we did not have any successful reactions or semi-successful reactions with pyrazole. We did have the one semi-successful reaction with triazole where we got a product. Something happened. We're not exactly sure what, but it's something we can use to move forward in our research. The future direction would be continuing to try and optimize these conditions that we have, whether it be changing the solvent, using a different metal precursor, so on and so forth, in order to actually metallate this ligand to a metal. And once we are able to do that and to classify it through our Nmr analysis, we will be able to try and use this complex in further new chemical reactions or reactions that we would expect it to have catalytic activity, and discover how well it is as a catalyst, how efficient it is, and if it's a good project to continue moving forward with. Thank you for listening to my presentation. Have a great day.